respect to x, Amber will be with respect to t. Every time. But then you'll be doing a lot of this stuff right here. Except it won't say dy dx. Maybe it's letter R, you'll write dr dt. Maybe it's letter A, you'll write dA dt. Maybe it's volume V, you'll say dV dt. Do you follow me? You'll continually be doing this throughout the problems. Because you'll be going, oh, I gotta differentiate this. Oh, it's with respect to time. You'll do a power rule, and Amber, and then right after it, you'll write like dr dt, or dA dt, or dB dt, so you'll get used to it. But every time, we're finding how fast the related rates, this is rate of change, right, with respect to what? Time. How fast things are changing. Maybe someone's pouring soda into this container here. Maybe someone's draining what? Coffee from a conical, a coffee machine. Maybe someone's pouring water into something. Maybe someone's blowing up a balloon, They're sitting there like, and the balloon's getting bigger and the volume's changing. Oh, area of a rectangle's changing. Let's spend 2 days on this because every geometric figure is going to change, right? Could be area, could be volume. Could be a square, could be a circle, could be a sphere, etc. Cool, so let's spend a couple days, make sure we got all this stuff down. So let's start with something simple. Okay, if I start with a circle? Will that work? Circle's simple, all right, we'll start. What do we want to change? Circumference, how about we change area? We'll talk about how the area of the circle is changing. Cool. Maybe the circle's getting bigger, maybe the circle is getting smaller. In my case, everyone, let's have it such that the area is getting bigger. All right, the area is changing in the circle. Can you give us a real life application? The closest I can do is skin cancer, everyone, but it's not really usually a circle. It usually looks like a blob, especially with me with all the basal cell skin cancer I've had. But what happens, everyone, if you don't have it taken, cut off? You know what it does? It does grow in size. It will. It'll start out like this little, it's usually pink in color, it might bleed. This little thing, a couple months later, everyone will be bigger and bigger and bigger. It'll form up on my shoulder and stuff. And I can pull this down, you see like something cut off. And it finally got cut off when it was about this big. It's not a perfect circle, but it's typical like that. So in our case, let's just say this circle is increasing in size, all right? And how fast is it changing? Let's say the radius is increasing. I'll do centimeters. 2 centimeters per month.
2 centimeters per month.
That sound good? Per month? Every month, the radius gets what? How much bigger?
2 centimeters.
2 centimeters. And the area gets bigger. All right. And then my question is, right, how fast is the area of the circle changing? When the radius is equal to 10 centimeters. So we'll start with the circle. By the end of Thursday, everyone, Thursday evening, you and I will probably cover it. So many different geometrical figures. Right triangles, spheres, rectangles, right? 2-dimensional, 3-dimensional. This one's just 2-dimensional. All right, now if you wanted to draw this out, you could keep drawing what? Circles that kept what? Getting big, right? Now what's going on? Changing it every month. Every month, that's how much it's increasing. So what do we start out with in every one of these problems?
The
That's the
area.
hard part. You gotta know your geometry figure and formulas. But I think if we just know the basics, we'll be good. Everyone know area of a circle?
Pi r square.
Let's write it down. We can make a list, everyone feel free to make a list throughout the whole, today and tomorrow, every time you're like, I didn't know that. Area of a circle is pi times r squared. So you start with the formula. I mean, if it was volume of a cone, we would have written volume equals 1/3 pi r squared h. And don't freak out if you're like, gosh, I don't know the volume of a cone. We'll list them. We'll make a list like, what one should I know? Amber, so I know all the geometrical formulas and volume and area at nights. The next step, everyone, we're going to differentiate both sides of the equation with respect to what letter?
T.
T. That's what we'll do next. So let's go over here and write dA dt. Cool?
Mm-hmm.
What are we going to write? We're going to differentiate all this with respect to what letter?
T.
T. But what's interesting? That's not T. That's a what?
R.
R. So we're going to do this just like we did implicitly. That's what we're doing. Implicit differentiation. It's almost like you can think of this R with the parentheses. And what do? I do the power rule. Because that's just a constant, right everyone?
Mm-hmm.
You don't need product rule, that's pi. Pi is not a variable. So multiply the 2 in front. 2 pi. Decrease this R by what?
1.
1. Or this time I won't put the 1 there. Right? And then chain rule, right next to it, guess what I'm going to write?
D. A. D.
The derivative of R with respect to that letter. Derivative of R with respect to T. dr dt. You go, why? It's because of chain rule. Why? We're doing implicit differentiation. Did anyone see that?
Mm-hmm.
I differentiated in R. So before with the x and y, every time there's a y, we put dy dx. Every time you got some variable that you differentiate, right after it, put d block dt. It was a big dv dt. Right? Now, how fast is the area of the circle changing when the radius equals 10? So we're solving for that. And that's what that means. d dt is a rate of change. So you're finding the rate of change of the area. So this is what we're solving for. Only thing we got to do is plug in 2 numbers. We got to plug in a number right there and a number right there. What goes in for R?
10.
10. And what goes in for dr dt? 2. Now is it 2 positive or negative?
Positive.
Good. Because everyone, if they said decreasing, I would have made that 2 negative. Do you follow me? It's something to remember today, tomorrow, even Monday. Just go, ooh, related rates. If some dimension is decreasing in size, I'm just going to make the rate negative. That means it's decreasing. The rate is decreasing, okay? You'll get used to it
So
though.
I feel like in this case, the R is like the Y.
That's right.
Right?
That's right. But get ready for other letters, but every time treat it like that. And we always do D what? DT.
DT. So like the whatever, the one with the like the third power, second power.
That's
like
right.
the number that goes when you're doing the change in.
You got it. And before I write that answer, Amber, you got it. Look at this. And that's just a little square, right? Did you know area of a circle is side squared? Do dAdt on this thing. Watch how you can do it. You would say what? dAdt. All right. And then differentiate that with respect to t. But that's an s. Well, do your power rule.
So it'd be
2 in
S
front,
over
decrease
DT.
s by what? 1. Then d what letter? ds.
S over DT.
There you go. You're an expert. You got it. You got related rates down. Why do we spend 2 days? Because every figure is going to change, right? We'll have a couple ships going like this. What shape is that? We'll have to make a picture to figure it out. Good job. Hey, so what's my final answer? Let's put the units. 40 pi
Centimeter
centimeters
per month.
per month. Did I miss anything, or is it centimeters squared?
Centimeters squared.
Brilliant.
Squared,
Now, once you look carefully, you go, what am I finding? What's changing?
Area.
Area. Area is squared centimeters, right? So centimeters squared per month. Right? You go, where did you? Well, that had a centimeters per month, and that had a centimeters. That's why. Everyone, if you wanted to put your units in here, there was a cm here, and there was a cm per month there. That's why it came up like that. Cm times cm, cm squared. Does everyone get that? Yeah. Cool. Did you want to do an area of a square that shrinks? All right. Don't worry, I'm going to give you that worksheet. And the problems I picked from the textbook, I hand-picked them, Kel, so they're all good, and we can work some of those or tomorrow and stuff. Even Monday. So if I don't get every related rates problem that you wanted work from tomorrow, you make me do it Monday.
So our test is.
All right, this is a square, and this time, let's say the side of the square is decreasing (5 centimeters this time everyone per minute. And when how fast is the area of the square changing when the side equals, make up any number you want, Amber. Give us some length. When the side length is what?
4.
What was it?
4.
Wow, if it's 4, then a minute later it won't exist, you agree?
Oh.
Isn't that cool though? You know, I think logically, that's okay. But a minute later, that square would be what? Gone, do you agree? Because if it's decreasing 5 centimeters per minute, a minute after, but that's okay, I'll put it. When the side length is 4, I just thought she was gonna say something like 400. That'll work. But we are making the observation, hey, a minute later, no more square. Okay, what's A equal to? S squared. D82. What do I do here, Amber?
2s
2s, now D.
s dt.
Yes.
over dt.
I put my 2 back here. The S is the 4 that Amber came up with, everyone. How do I write ds dt? How do I write that? Because it's decreasing.
So the 5.
Negative 5. So that means my answer is negative. And when dA dt, my final answer is negative what?
5 times 2 is 10. 40
Centimeters or centimeters squared?
centimeters square per minute.
Per month or minute?
Minute.
Per minute?
Mm-hmm.
But it's negative. What's that indicating? It's indicating that the area of the square is what? Shrinking at that moment. Remember, this is still instantaneous rate of change. At that moment. Okay with that? All right. The textbook problems, everyone, they're great. But this is one of those sections. Let's do like a few problems together. So I mean, this worksheet's got 3 problems. I think I left you enough space to write on here. If you'd rather write in your notebook, just feel free to write these in your notebook. Let's do 3 of these together. When we're done this sheet, I think you'll see triangles. I also think you'll see cones. You're welcome. And yours, Sarah?
Oh, they had an orientation. So both of
She
them.
probably told me about that and I forgot.
Yeah, so both of them. Yeah.
Can you borrow your notes?
Yeah, recording.
Oh, thank you so much. Oh, awesome. You're recording?
Yeah.
Hi, Sarah.
Anything else you want to say?
That's about it. Hope you have a good orientation. Very tall, though. Hey, you're welcome. Amber, should I give you a copy of this to give her?
Oh, yeah.
Hey, you're welcome.
You too.
How many copies?
You too, or she wasn't on you.
Oh, that's right. I'll say hi, Richard. Hi.
And 2. 1, 2. There you go.
2 copies for them. All right, everyone. We're gonna have to make some pictures in a section, right? Pictures tell us the story. So read through that problem. If you have to, reread it, right? I do want to give you a heads up. You get a lot of right triangles. Not every problem, but you get a lot of them. Just because of how things move. Ship moves this way, ship moves that way. Plane's flying this way. I'm standing here and then the plane flies over me. And you see how that distance changes. You don't see a right triangle?
Mm-hmm.
Or a train passes by. I'm standing right here. Here's this one again. The train comes by and goes like that. You're like, okay, how far is that changing? Planes, trains, automobiles, you bet. You will get a lot of right triangles. I know. Have you seen that movie? That's good. That's very funny. He's going the wrong way. Going the wrong way. How does he know it's real?
Is that a Steve Martin?
Yes. Tony's going the wrong way. You're going the wrong way. Let's see. All right, let's look at this first one. A police cruiser approaching a right-angled intersection from the north. All right. Here comes the cruiser. A right angle, I guess that'd be like that, huh? There's the intersection. Here comes the cruiser approaching from the north. So you can make a police car if you want. There's the police. Chasing a speeding car, has already turned the corner, is now moving straight east. So the car's down here. They still chasing those guys in New York?
Oh, yeah.
So they haven't caught them?
Nah,
They might be in Canada then, right?
could be, yeah.
If they're in Canada, they're gone.
Did you see them leaving a smiley face for the police?
Yeah, I know.
That was funny.
It's like something out of a movie, like Shawshank Redemption. Escape from Alcatraz. All right, and here's the speeder. I'll just call him Dude. All right. He's going this way. The dude's going this way, right? I got some numbers here. When the cruiser is 0.6 miles north of the intersection, the speeding car is 0.8 miles east to the east. The police determine with radar the distance between them and the car is increasing at 20 miles per hour. Oh, the distance between them is increasing, they said.
Mhm.
I see we draw a line about that. I want the distance. What shape do you see? Right triangle.
Triangle.
What's Pythagorean there? So you might be using that a lot. 3.8 or 3.9. Yeah. A squared plus B squared equals C squared. And Amber, we're talking about after we do this, eventually we'll get a dAdt, we'll get a dBdt, and we'll get a what? dC to T, right everyone? That's what we'll get when we differentiate. You'll get a little dAdt off to the side once you differentiate in dB. That's what'll happen. If you don't like A, B, and C, you can use other letters. But in this problem, what has to be length C?
Hypotenuse.
Good. All right, this has to be C. I don't think they give it to me. I don't think they give it to me. I do believe they gave me A and B though. Because they're always asked this question at one instant, okay? And it was at the instant when he was 0.8 miles to the east, and this was 0.6, right?
Mhm.
0.6 mile, 0.8